welcome to the 11th lecture of optical sensors course. In the last turn we discussed what are plasmons and what are surface plasmons, what kind of waves these are, and we saw that when it comes to bulk plasmons they are basically longitudinal oscillations. However, these surface plasmons are decaying waves which are travelling at the interface of a metal and dielectric, and we solve for the dispersion relation for this kind of wave, and we drew two important conclusions. One was that this kind of wave can only be excited at the interface of a metal and dielectric, I mean a material interface which has dielectric functions of opposite signs, and the second thing was that it can only be excited by a p polarized wave. In the present lecture we will discuss it further and we will see how do we excite surface plasmons. Also, since it is a decaying wave, we want to know what is the penetration depth and what is the propagation length of these waves. So, since the dielectric function of the metal is complex, the wave vector which is kx, we were solving for the wave which was this was z and this was x. So, wave is travelling in x direction. So, basically it has complex nature because k is a function of epsilon m, k is a function of epsilon m. So, if epsilon m is complex, basically k will also be complex. So, you can put epsilon m1 plus I epsilon 2 m2 in this relation, and then you can separate out the real and imaginary parts. This is real part of the wave vector and this is imaginary part. And what you see is that it is almost same. So, the basic nature of the this is the one which is responsible for the propagation of the wave. This is the one which is the component which is responsible for the wave to die out while it propagates. So, when to the length where the intensity of this wave becomes 1 by E square, amplitude to 1 by E and the intensity becomes 1 by E square, that length is called propagation length, and that is defined like this relation. LSP is inversely proportional to inversely equal to 1 by 2 kx imaginary part. So, it depends on the imaginary part of the dielectric function like this, and real for the real part it is inversely proportional. So, you can see that the decay will be faster if the absorption is faster. So, the LSP will be smaller. For example, I have given two values for at lambda is equal to 543 nanometer and 633 nanometer. For gold air interface, the propagation length is about 10 microns, while at higher wavelengths it is 15 micron. So, and similarly for silver air interface this is about 30 micron and 44 micron. So, you can see that for silver the propagation length is larger, that means the absorption is smaller. So, if it absorbs less, the surface plasmon wave can propagate to a large distance before it dies out. So, if you want to make a waveguide for surface plasmons, you want to prefer a material which has smaller losses, so that the penetration depth, the propagation length is larger. So, it propagates to a large distance, but in this particular case we will have miniaturized sensors. So, you can see that you have all you need is about a 10 micron size film, and it will still work as a sensor, because you have a wave which dies out after moving to 10 micron or so. So the structures which are involved in this particular kind of propagations in configurations are very small in dimensions, and if you have around 50 micron or so, that is fine. But if you want to make a waveguide of metal and propagate some light which gets coupled into surface plasmons, then it will die out only after 50 micron. So, one has to choose some material which is better in terms of propagation length. And penetration depth, if we assume that the imaginary part is much smaller, then we can define the penetration depth like this. This is the expression for penetration depth into the dielectric medium, and this is into the metal, and you can see that from here, as we told that the field decays both exponentially in the metal and in the dielectric, and when up to the value when it becomes 1 by E of the field at the interface, then it is called the penetration depth. So, up to the distance where it becomes 1 by E. So, you can see that the penetration depth in the dielectric is larger than that of metal, and that is because of the absorptive nature of the metal. So, since it is absorptive, the field dies out quickly into the metal region, while for the dielectric it is larger. So, let us see some numbers. You can see that at 543 for gold and air interface, the for metal only it is 26 nanometers, while for gold for air it is 250 nanometers. So, you will have a penetration of about 200 to 300 nanometers in depth. So, if you put an analyte which is larger than this, it will not sense it completely. So, there are special methods you have to choose. So, this is basically a wave which is travelling at the interface, and its field is only about 200 nanometers into the dielectric medium, while in the metal it is even smaller, it is about 26, 30, 23 nanometers or so. So, it dies out quickly. At larger wavelengths, you can have larger penetration depth, and in both the media, which actually for metal it is not much affected, but for the dielectric it is affected a lot due to the same reasons, and then you have better penetration. So, if we want to see that when you increase the penetration depth in the infrared, it becomes even further larger. So, what you have plotted here is the penetration depth in the sample in microns, and penetration depth in the metal in microns. You can see it is very small here, while it is much larger, and if you move it to infrared wavelengths, it is about 10 to 20 orders of magnitude larger for infrared. So, you can see these wavelengths here, right. Surface plasmon wave vector. So, we already derived this expression for surface plasmon wave vector, where epsilon s is the dielectric function of the dielectric, epsilon m is the dielectric function of the metal, and omega by c was a constant, or you could write it k 0. So, if you plot k versus omega curve, what you see is that for a light travelling in a dielectric medium, it is a straight line. This is called light line. However, so for light travelling in this medium, suppose I have an interface where we have a dielectric, suppose this is air, it is a dielectric and it is metal, and then we have incidental wave. So, it will have k is equal to omega by c, and that will be a straight line. So, omega by c basically is equal to k. So, the omega versus k curve, or omega, let us say this way, omega versus k curve is C, which is constant. So, its slope is constant. So, you will have a straight line. However, for surface plasmons you see two branches, one is here, another one is here, and in between this and this you have forbidden a gap, there is a gap, you do not see any branch here. So, what does it mean? It means that for this region there is no surface plasmon. So, if you remember, when we plotted for the dispersion curve for the bulk plasmons, it was like this, this was the straight line and this was the curve. So, this curve is similar to here. So, omega Pb is the plasma frequency for bulk metal, and for omega values greater than omega Pb, omega greater than omega Pb, all the modes are radiative. So, you have bulk plasmons, bulk plasmons. However, for values which are smaller than this value, we will come to how to get this value, and for these values this is non-radiative. So, omega less than omega p by root 2, it is non-radiative. So, how we arrive to this value omega Pb by root 2, let us see. So, we have epsilon omega is equal to 1 minus omega p square upon omega square. We had this value, and also we have Ksp is equal to omega by c under root epsilon s epsilon m divided by epsilon s plus epsilon m. So, we can write it in terms of omega p, and so you will get it from here. If you have epsilon omega, epsilon s is equal to 1, which is for air, you will have Ksp equal to omega by c under root epsilon m upon 1 plus epsilon m, and here we have, we want to calculate omega and in terms of omega p. So, if you put epsilon m at resonance, epsilon m is equal to minus 1. So, the resonance condition is epsilon s plus epsilon m is equal to 0. This term has to be 0 for resonance to happen, and epsilon s will be equal to minus epsilon m. So, here if epsilon s is equal to 1, then epsilon m is equal to minus 1. So, if you put minus 1 is equal to 1 minus omega p square upon omega square. So, it will be minus 2 is equal to omega p square upon omega square. If you take it here, so minus minus cancels out, you will have omega is equal to omega p by root 2. So, basically if we have omega p b, if you put b here, b for bulk, because we will discuss nanoparticles also, we have changed it to omega p b. So, you have omega is equal to omega p b by root 2. So, this is the asymptotic value. So, you have the asymptotic value of omega, which becomes omega p b by root 2, For these values only you can have surface plasmon excitations, asymptotic values. Okay. There is something more important, and that is that you can see that if you sign this, suppose you have this interface of say dielectric, say this is air and this is metal, and you shine light, you see that the wave vector, and if you shine by laser light, you can see the wave vector of laser light is much smaller than the wave vector required for surface plasmon excitation. So, here this is called phase mismatch. So, you want to have, so suppose it is like this, you have this interface. So, I am wearing a gold ring. So, you have air and water interface. If I shine laser on it like this, can I excite surface plasmons? That is the question. So, this kind of interface supports this kind of modes, surface plasmon modes, but how do we excite them? Because we have seen now that the wave vector of this light which is impinging on this interface is much smaller than the wave vector required to excite surface plasmons. So, this is an issue. So, we know already that this kind of interface as a metal dielectric interface supports an electromagnetic wave which is surface plasmon wave which is travelling along the interface. So, we already saw the wave vector for surface plasmons is given by this black line, while that for the light line it is straight, this is the red one, and when you want to shine laser on this interface, there is a mismatch between the phase between these two, and because of this mismatch you cannot excite surface plasmon. So, somehow we want to increase the wave vector from here to match this condition, and to do that what we do is that we make it very thin and bring out a prism of high index there. So, the NP is high index prism. You bring a high index prism where the which is kept very close to the metal, and you fill it with the dielectric, and you shine from one of the ends and you measure the light which is getting reflected from here. So, this is incident ray, this is reflected, and what you see is that if you change the angle, there should be some condition when you have the resonance. So, what happens actually, let us see. So, when you pass it through the prism, basically you will have total internal reflection as I told you earlier, and you will have evanescent field here, this red one. This evanescent field will interact with the metal dielectric interface here, and that if has the wave vector which is equal to that of the surface plasmons, you get a resonance. So, what happens actually when it passes through the prism material as a function of angle, because there is a multiplication of NP, you increase the wave vector, and at that certain value of theta for that particular frequency you get a resonance. So, what happens, what will you see in the reflected light? So, if you measure the reflected power as a function of theta at that particular value, when this matches, when this intersects this light line, when it intersects this surface plasmon wave vector curve, you get a resonance dip for that particular refractive index of the dielectric medium. Now, what happens if I change the the refractive index of the dielectric medium from N1 to N2, say N1 to N2, then the nature of the dispersion curve for surface plasmons will change. So, now it is the green curve, and we have considered that N1 is greater than N2, sorry, N2 is greater than N1. So, now for this same incident light, we need to match the phase again, and to do that we need to keep the changing the angle. So, then let us say it moves from A to B, and then you have a resonance again at theta 2. So, if you increase the refractive index from N1 to N2, you have to increase the angle of incidence from theta 1 to theta 2 to match the resonance condition. So, there is a shift, and it is a red shift. So, there is a red shift in the resonance angle. Also, and this is the resonance condition which is satisfied for now theta 2. Okay. Now, what happens actually if I do not use a monochromatic light? So, this was the omega was fixed and this was monochromatic light. So, it was like laser, like this laser, yeah, like this laser. Now, I do not want to use a laser, I have a polychromatic source. Now, let us say what happens with a polychromatic source. Polychromatic source. So, you shine at an angle theta, and now you do not want to change the angle. So, you change the wavelength lambda. So, if I change the refractive index from N1 to N2, what will happen? So, there are two parameters, one is theta, one is omega. I fixed omega in the first case and theta was varying. Now, I fix theta and omega is varying. I have a polychromatic source. So, what will happen at particular angle of theta 1, we will have a resonance for this particular value of omega, and we will have a dip. Now, I move from N1 to N2, we will have a different dispersion curve, which is the green one. Now, we had a black one, now we move to green one, but this intersects it here. So, what I can do is that I can move from A to C, rather moving A to B. We do not need to change the angle, then it is on the fixed angle, but we change the wavelength. So, you change the spectrum, you do not change the angle, and then what you measure is that is change in spectrum. So, that is called spectral interrogation. Again it shows a red shift, right. So, there are two ways to do a sensing. One is called angular interrogation, where you measure change in theta with respect to change in the refractive index, and another one is spectral interrogation, where you measure change in lambda with change in refractive index, and that is how you define the sensitivity. So, if a beautiful lady sitting there asks me if I can excite surface plasmons on my earring, which is made of gold, the answer is no. you cannot excite simply shining surface plasmons by simply shining light on it. For that you have to have some arrangement to match the phase of surface plasmons with the light which is incident on the interface. Here I showed you that can be matched using a prism which has high refractive index, and you measure the change in angle, and from there you can say how much change in refractive index occur, and that is how you use it for sensing. So, there are two important configurations, one is called auto configuration and another one is Plasmon configuration. So, the previous one which I talked about was auto configuration, where what we did is that we had this metal and dielectric interface and we brought the prism very close to it, and how close? About 1 micron or so. If you remember, when we calculated the penetration depth for the evanescent field, it was only about hundreds of nanometers. So, in this particular case, if you want the evanescent field to penetrate through here and intersect with this interface, this gap has to be really small, very small, and for this has to be small, you have to bring the prism very close to the metal surface. That is really very difficult sometimes, to manage such a small gap of only few hundred nanometers or so. Okay. So, that requires lots of skills, but this technique is good for measuring the flatness of metal films. You bring it close, and if at all the places the surface plasmon response changes, because it will be as a function of distance, you can say that the metal film is not flat. So, this technique is somehow useful. However, most of the people use something called Plasmon configuration, where what you do is that rather making a gap, you put the dielectric otherwise and make the film very thin metal film. So, you have very thin metal film which is only 50 nanometers or so. So, if you have such a thin metal film, the evanescent field still can penetrate through and excite surface plasmons at this interface. So, you have surface plasmons at this interface. Also, you have to understand that this is also a metal dielectric interface, but light coming from here, from this medium, will again have dielectric constant, propagation constant, which is much smaller than the propagation constant of the wave of the surface plasmons for this interface. So, that is why light coming from this medium cannot excite surface plasmons at this interface, but only at this interface. Okay. Now, if you change the refractive index of this medium, you can excite surface plasmons at this, you can have different resonances. So, that is why Plasmon configuration is very useful, because it is very easy to fabricate. You can directly coat the a thin layer of metal on the prism surface. This one is difficult because it is very difficult to bring the prism very close, nanometers close to the metal film, and also fill the gap with different refractive indices. This is challenging, but this one is easy. There are other configurations. I already talked about the Plasmon one. So, here it was like you have incident field beam which excites evanescent waves, which eventually can couple to surface plasmons waves, and this dielectric medium can be used as a sensing medium. You can change the refractive index here and you measure the power in the reflected beam as a function of angle of incidence. Other method is grating based coupling, where light at incident at an angle theta will have different orders of reflection, reflected light, and this different reflected orders will have different wave vectors. So, it will, if it is in forward direction, this will be a plus sign, if it is in backward direction, this will be in minus sign. This is the wave vector of light incident through this medium, dielectric medium, and this is the wave vector which gets added due to the diffracted orders. And when this becomes equal to that of the surface plasmons supported by this interface of this metal and dielectric, then that order goes missing in the reflected light. So, you do not see any that particular order, you see that particular order getting missing from the reflected light. So, that is how you excite surface plasmons using a grating. In a waveguide, again you can have this evanescent field. So, basically there was a prism encashment configuration and that was having this evanescent field. What you can do is that you can remove a small part of the cladding and do a coating of metal, and then this evanescent field from the waveguide metal interface will excite surface plasmon waves at the dielectric and metal interface. Similarly, what you can do is that you can take a small portion of the cladding out from an optical fiber and do a thin layer of coating of the metal on the cylinder. So, this is only very thin. So, again it will have evanescent field because of total internal reflection. So, it can excite surface plasmon waves at this interface, at the interface of the metal and the sensing medium. So, when we are sensing with monochromatic light, we do angular interrogation, as we discussed in the Cashman configuration. You change the angle and you measure the reflected power, and what you see is that with an increase, with the change in angle, you see how much change, with a change in refractive index, you see measure actually how much change in angle occurred, and by measuring this you can say that what is the change in refractive index. But that is a difficult technique. I mean, what you do is that you have a prism and you keep on changing the angle. So, you keep on changing the angle. So, you have to rotate the prism, you have to rotate the prism, or you rotate the incident beam, whatever, and then you rotate this detector. So, this is a difficult problem. I mean, it needs mechanical components, all that, because you have one directed beam, and if changes angle theta here, then it will be deflected by 2 theta, and you have to adjust the detector all the time. To avoid this, what you can do is that rather sending a beam which is collimated, you send a diverging beam. So, here you send a beam which is making an angle theta. What happens actually, now it has a range of angles, and when you have a surface plasmon resonance, you get a dark line here. So, what you do is that rather using a detector, you use a camera. So, you do the image. So, you get the image of it. So, if the beam was was all bright, the angle for which when you have surface plasmon resonance, it will go missing here and you will get a dark line there. Later you can do image analysis and you can find out the width of the dip and where the position. If you can measure the pixels, you can know where exactly is the dip. So, this is a more advanced technique, and based on this only most of the companies are using this technique only to make SPR devices, say for example photonic CIS. Photonic CIS company is using this, Biocor is using this. So, there are many companies which are using this kind of technique. Other way of doing that was using a polychromatic light. What you do is that you have a source where now we are using a polychromatic source with optical fiber, and light coming through it can be collimated using an achromatic lens. You put a polarizer which polarizes it at for a p polarized light. With an aperture you can control the width of the beam, and then it falls on this interface of metal and dielectric. You have an light here, and then you collect the light and goes to the spectrometer. So, rather measuring the angle, you measure the wavelength, and by measuring the shift in wavelength you can say how much change in refractive index occurred. So, there are these 2-3 methods. There are others also we will discuss in the next talk. So, let us summarize what we studied today. So, what we did is that we obtained the expressions for propagation length and penetration depth of the surface plasmons and discussed them, and we also discussed the dispersion curve for surface plasmons and found out what are the issues which need to be resolved to excite surface plasmons. And then we discussed various methods for exciting surface plasmons and how we use them for sensing, and also we discussed various modes of operation for this kind of sensors. Thank you.